Hello. In today's lecture, we'll establish the non-existence of finite fields of certain composite orders. And in the next two lectures, we'll establish the existence of finite fields of the remaining composite orders. The main tool we'll use is the characteristic of a finite field, which I'll define next. Let f be a field. The characteristic of f, denoted by char f, is the smallest positive integer m, such that when you add 1 to itself m times, you get the additive identity element 0. Of course, such an m may not exist. If it doesn't, we'll define the characteristic of the field to be 0. For example, the field of rational numbers, the field of real numbers, and the field of complex numbers have characteristic 0. This is because if you add the number 1 to itself in these fields, you get the numbers 1, 2, 3, 4, 5, and so on. And this sequence never reaches 0. On the other hand, the field of integers modulo p, where p is a prime, has characteristic p. And this is because in the integers modulo p, if you add 1 to itself repeatedly, you get 1, 2, 3, up to p minus 1. These are all distinct elements and non-zero. And the next element in the list would be p, which is the same as 0 modulo p. I'll next prove two properties of the characteristic of a field. The first property is that if a field has characteristic 0, then f is an infinite field. In other words, all finite fields have non-zero characteristic. To prove this, I'll consider the list of elements you get by adding 1 to itself repeatedly. This list contains the element 1, 1 plus 1, whatever that is, 1 plus 1 plus 1, and so on. I claim that the elements in this list are distinct. Suppose otherwise, that the element 1 added to itself a times equals the element 1 added to itself b times, where a is less than b. If this is the case, then subtracting the first element from both sides gives us 1 added to itself b times minus 1 added to itself a times equals 0. But this element is simply 1 added to itself b minus a times, which we see is 0. Since b minus a is a positive integer, this contradicts the assumption that the field has characteristic 0. And that proves the theorem. I'll next prove that if f is a field with non-zero characteristic m, then m must be prime. So in other words, all fields have characteristic that's either 0 or a prime number. So there do not exist any fields of composite characteristic. To prove the theorem, suppose m is composite. Let's say m is a times b, where a and b are proper factors of m. Let S be the field element you get by adding 1 to itself a times, and let T be the field element you get by adding 1 to itself b times. Note that both S and T are non-zero, since A and B are both smaller than the characteristic. So now, when I multiply S times T, I get this product. I can multiply the ones by themselves a total of A times B times to get 1 added to itself m times. Since m is the characteristic, this sum is 0. Hence, S times T is 0. I noted that T is non-zero, so T has an inverse. Multiplying both sides of the equation by T inverse gives us that S times T inverse, which is just S, equals 0. but this contradicts our observation that S is non-zero. And so we conclude by contradiction that M is prime, and that proves the theorem. We're ready now to tackle the main question of this lecture, which is the non-existence of finite fields of certain composite orders. The tool we'll use is linear algebra. We'll do this by showing that one can always view a finite field as a vector space over a certain subfield, the subfield being the integers modulo p, where p is the characteristic of the finite field. Recall then that every vector space has a dimension, the dimension being the size of any basis of that vector space. That will immediately give us the answer to our question about the non-existence of finite fields of certain composite orders.
Video lecture V9c reviews basic concepts from linear algebra that we will use throughout this course. I recommend watching this video if your linear algebra is a bit rusty.
All right, let's proceed. I'll first introduce the notion of a subfield. I'll do this informally. Let F be a finite field of characteristic P, where P is a prime number. I'll consider the subset of elements of F, which I'll call E. The set E is defined as follows. It contains 0, 1, 1 plus 1, 1 plus 1 plus 1, and so on, up to 1 added to itself P minus 1 times. The elements in this list are distinct because the field has characteristic P. And the next element in this list would be 1 added to itself P times, which is the same as 0. Again, that's because the field has characteristic P. One can now verify that the set E is also a field using the same operations for adding and multiplying elements as is done in the field F. E is called a subfield of F. To reiterate, the set E is a subset of F. And it's a field itself with the same addition and multiplication operations as the field F, but restricted to elements in E. Now, if you identify the elements of E with the elements of the integers modulo P in the natural way, so I'll call 1 plus 1, 2, 1 plus 1 plus 1, 3, and 1 added to itself P minus 1 times the number P minus 1. This is just a relabeling of the elements in E as integers between 0 and P minus 1. One can see that E is essentially the same field as the field of integers modulo P, except again that the elements of E might be labeled differently. Putting this all together, we've proven the following theorem. Let F be a finite field of characteristic P. Then the integers modulo P is a subfield of F. All right, so let's now see how we can view finite fields as vector spaces. Recall that a vector space must contain vectors, scalars from a field, and have notions of vector addition and scalar multiplication. So let F be a finite field of characteristic P, where again P is a prime number. And recall that within F, we have the integers modulo P as a subfield. We now identify vectors as being elements in F, and scalars as being elements in the subfield of integers modulo P. We can define vector addition simply as addition of elements in F. And similarly, we can define scalar multiplication, that's multiplying a vector in the vector space F by a scalar in the field of integers modulo P, to simply be multiplication of the field F. So we now have notions of vectors, scalars, vector addition, and scalar multiplication. One can then check that F is indeed a vector space over the integers modulo P. In other words, the axioms of what it means to be a vector space are all satisfied. These axioms are easy to verify because they are essentially inherited from the fact that F is a field. You can find a list of these axioms in an appendix of the course textbook. We're ready now to prove our main theorem of the lecture, namely the non-existence of finite fields of certain composite orders. Let F be a finite field of characteristic P, where P is prime. Then the order of F is P to the n for some positive integer n. So this theorem says that all finite fields must have an order that's a power of a prime number. And so finite fields of orders that are not powers of prime numbers do not exist. Let's prove the theorem. So recall that F can be viewed as a vector space over the subfield of integers modulo P. All vector spaces have a dimension. I'll let the dimension of F as a vector space over Zp be n. Now the dimension of a vector space is the size of any basis for that vector space. I'll let alpha1, alpha2 up to alpha n be a basis for F over Zp. Recall that a basis is a linearly independent spanning set, and hence every element beta in the finite field can be written uniquely as a linear combination of the basis elements. Here the coefficients in the linear combination are elements in the field of scalars. Thus, the elements of the field F are precisely the set of all linear combinations of the basis elements. Now, there are n scalars C1 through Cn, and p choices for each of these scalars. Each choice of scalars gives us a unique element in the field, and hence the number of distinct field elements of this form is p to the n. This proves that F has order p to the n. As a corollary of the theorem, there do not exist finite fields of orders that are not the power of a prime number. So, for example, there do not exist finite fields of orders 6, 10, 12, 14, 15, and so on, because these numbers are not powers of a prime number. The question we'll tackle in the next lecture is the existence of finite fields of orders that are not prime but prime powers. So we'll ask whether there exist finite fields of orders 4, order 8, 9, 16, 25, 27, and so on.
In the next video lecture, we'll introduce polynomial rings, the ring of polynomials, modulo a polynomial f, and we'll use these rings to establish the existence of finite fields whose orders are prime powers. Have a great day, and I'll see you in the next video lecture.